Hello, everyone. It's my great pleasure to introduce to you my dear friend, Dr. Regina Finsterhölzl, in the name of TNG. Welcome for joining us here at BTD 24. It's a great pleasure to have you here. Regina will talk about quantum computing and how it works in principle and practice. Let me talk a little bit about Regina. She has done first a PhD in history at the Humboldt University of Berlin, in the course of which she also wrote a book on decolonization in Western Africa. But not satisfied with that, she also did a PhD in theoretical physics afterwards at the Technical University of Berlin, where she worked on quantum optical systems and systems of coupled qubits. Currently, she holds a postdoctoral position and a lecturer position at the University of Constance, where she's working on quantum information processing in solids using spins in diamonds as qubits. She's also working on protocols for the control of and manipulation of quantum information with a focus on quantum error correction codes and quantum algorithms for near-term quantum computers. Outside of academia, Regina has also worked for the Institute of Innovation and Technology in Berlin as an expert for quantum computing applications. I befriended her, or we got friends, when I was doing a postdoc in Berlin at the Technical University, when she just started with her physics degree, and now, as I said, she's holding a postdoctoral position. Today, she's going to talk about the current state of development and the potential of quantum computers. She'll also give a short introduction to quantum computers and quantum algorithms. Then she'll focus on current research in the construction of quantum hardware, and further will focus on the research of improving error-prone computations, and then for the parts that can't be improved, how you can correct for it anyway. For a short reminder for everybody who's joining us in a live stream, you can post your questions in the Zoom chat. We'll have a look at all the questions also here in the room at the end of the talk. With all of that, thank you again for joining us here at Big Tech Day, and please all of you give a warm welcome applause to Regina. Let's go.
Thanks very much again. Thanks very much, Jan, for the kind introduction, and thanks very much again for inviting me as a speaker today. Quantum computing, how it works in theory and practice, and let's jump right into it. I hope my pointer is working. It's a bit slow. Do I need to stand here? Maybe? Okay, I will probably better not use it. Okay, this was work done at the University of Constance and funded by the project QC4WW. Okay, so today's topics. We will cover the fundamentals of quantum mechanics, but only very briefly because Jens Eiser did it in a fantastic and very instructive way this morning, which is good because then we can build upon this talk and jump into what is a quantum computer and what are its promises. And the biggest part of my talk today is how does it work in theory, and the biggest part will be how does it work in practice. And I will introduce to you work on correcting errors on quantum computers, on really existing quantum devices. Okay, I will start with citing Richard Feynman, who is a Nobel laureate in quantum physics. I think I can safely say that nobody understands quantum mechanics, so this is a brief motivation for you for my introduction today. Please don't worry. You don't need to be able to follow everything. No, but what he was relating to was, of course, the interpretation of the laws of quantum mechanics, and to the fact that they differ quite fundamentally, or seem to differ quite fundamentally from our everyday life, which is governed by Newtonian physics. So the history of quantum mechanics, it's a relatively young discipline. In the beginning of the 20th century, we saw the first theories evolving on quantizing energy with black body radiation and the atomic model of Bohr. In a very stunningly brief time, the mathematical formulation took place. between 2 to 3 years. And in 2027, we had the Copenhagen interpretation, which is taught today at universities. So the postulates of quantum mechanics. So what is so fundamentally different about the everyday experience in life? So a quantum state is described by a complex number in Hilbert space, which is the vector space of complex numbers, and a qubit, which is a quantum mechanical bit, so it's the basic building block of a quantum computer, is described as a state in this space. So this is the bracket notation which we have here. And it can have the values of 0 or 1 as a classical bit. So classical is always the counterpart to quantum mechanical, so our normal everyday life. So a classical bit can have the values 0 or 1. And it can also take on these values, but it also can take on any superposition of these two. So it can be described by this bit here. And it's intrinsically probabilistic. So the complex coefficients in front of 0 and 1 have a probabilistic meaning, and their absolute squared is the probability to find the system in the respective state when you look in the spaces. So when you observe it, and I will come to that in a second. So yeah, it's described on a unit sphere because we normalize it. And these states can also interfere, so the probability amplitudes can interfere. And if we have a wave with the same amplitude and frequency, then they can completely, depending on their relative phase to each other, can completely destroy the signal. So this is called destructive interference. Okay, so now we would like to observe the system. And an observable is also defined in Hilbert space. And what is so strikingly about a quantum mechanical system and is not known in a classical world is that when you look at the system, you will alter its nature. So if you measure it, you partially destroy the information about the qubit. And this was illustrated by Schrödinger in the 20s in a thought experiment, which we've also learned about this morning, Schrödinger's cat. Where he said like, okay, the cat is now our qubit, so the cat behaves as if it was a qubit. And we place it in a box, and then we close the box. And this means that we shield it completely from the environment. And then we kind of put a mechanism into this box which really intrinsically, probabilistically kills the cat, maybe. We don't know that. And then the cat is in a superposition state between dead and alive. If it was a qubit, it would really be in a state like this. And then the moment we open the box, we interact, the qubit interacts with the environment again, which is, of course, in reality, the cat always interacts with its environment. But if it was a qubit, and then if we measure in the basis dead or alive, then we would find it with the probability of the amplitudes here with which we have killed it in the state alive or dead. And we would have to repeat the experiment a few thousand times to really get an idea about these coefficients. And this is, again, the probabilistic nature of quantum mechanics, and it's also about that you interfere with this, you influence the system when you look at it. Then we have the no-cloning theorem, which means that we cannot copy a quantum state without destroying it. And then we have the uncertainty principle, which in principle basically means that we cannot observe a particle precisely where it is, and then if we observe it precisely, we cannot tell how fast it moves, because these are complementary quantities. Yeah, we have quantum information correlations, which are much, much stronger. They can be much stronger than the correlations in classical information theory can be. And so if you have a quantum register, then it is comprised of several single qubits, which we put together. And then this register of 2 qubits can take on a superposition of 4 states. And in principle, any register of n qubits can take on 2 to the n states. So the Hilbert space grows exponentially, which means that we have a quantum computer with 20 bits. We are already in millions and thousands of trillions of states which we can map with a register, which makes quantum computers already on a small scale, in principle, powerful tools. Now, if we have a 2-qubit state here, then if we have coefficients where we can write these 2 qubits still as a product of 2 single qubits, then we do not have stronger correlations than in classical theory. However, you can look at this state here and see that there's no way of writing it as a product state. There's no way of describing these 2 qubits as separate qubits anymore. And this means that the particles can only be described together, even if they're separated, which means that we have a non-locality of measurement statistics. And this is a very strong correlation, which is called entanglement. Okay, with that, we will jump into quantum computing, how it works in theory. So, what is a quantum computer? We've heard it this morning, a quantum computer is a computer, but it's one that functions on the basis of the laws of quantum mechanics. And its carriers of information are quantum bits, not bits, but quantum systems which are controlled, coherently controlled on the scale of a small system, so on an atomic scale, on the scale of a spin, on the nanometer scale. And the hardware must be built in such a way that these physical systems can be observed and controlled. So the current status is called noisy intermediate state quantum devices, noisy intermediate scale quantum devices, which means that we have small to medium-sized quantum processors, so around 20, 50, up to 1,000 qubits, which are still very error-prone. So all the operations on them and the qubits are still rather erroneous. Okay, we now assume we have our quantum system, which functions as a quantum computer, and we need to control. So we have quantum gates in the very similar way in which we have gates on a classical computer. And one of the specialities about operations, quantum operations, is that they have to be reversible. So they are reversible in order to be a quantum information, a coherent one, a quantum gate. And this means that all our computations we do on a quantum computer have to be reversible, which is clearly not the case always when you have a classical computer, when you do your computations. You can't always, from the result, undo the calculation. So we define the Hilbert space states here, and then in principle it's pretty straightforward matrix calculation to do a quantum gate. So this is a NOT gate that you can see here, and you can see that it would flip a state in the spaces to exactly its opposite. And if you look at this unit sphere where we describe our qubit, then you have here the basis states 0 and 1. And then if you apply a so-called Hadamard gate, then you flip to a rectangular basis, the X basis, which is in the basis of the superposition state, which I just explained to you. And this looks in matrix form like that. So much for the theory, for a single qubit gate. And we also need to be able to create entanglement, because it's one of the bases of many algorithms. So we do this by the so-called C0 gate. And the C0 gate, which is written in matrix form like this, and now we have a 2 to the n vector space here, so 4-dimensional vector space for 2 qubits. And the C0 gate will flip the target qubit based on the control qubit being 1. So this is the action on a 2-qubit register. And if with these 2 ingredients that I've just designed to you, you find your first simple quantum circuit here, which you can now understand. We have 2 qubits. We initialize them in the 0 state. To the first one, we apply a Hadamard gate, so we flip it in the X basis. And now, based on the condition of this state being 1, we also flip the second qubit, which will only be the case in a superposition state for the second part of the description. And with this, we've generated a maximally entangled Bell state. Okay, so what can a quantum computer do that a classical computer cannot? And we've also heard a lot of interesting aspects about this morning, so I will only very briefly say that based on these laws, we can construct quantum algorithms. And one of the nice things is that by means of superposition and interference, we have during one calculation, in principle, the possibility to evaluate the state of 2 to the n states in our vector space. This is, of course, only possible for certain calculations, but this is what is meant by quantum parallelism and makes it so powerful for some algorithms. And if we look at the big O notation, which is a statement about resource requirements, then we can say that we have, on principle, on paper, proven an exponential advantage for some linear systems of equation and factorization, and that other cases are not as strong, but they also offer an improvement. And currently the search is on for quantum supremacy or quantum advantage, where it has to be proven that a quantum computer can do calculation in a super polynomial speed up compared to a high performance classical computer. I will skip this due to reasons of time, but we can come back to this later, complexity classes and what a quantum computer can do, if you're interested in it. And this is also only very briefly because we had it this morning, so we can try and use a quantum computer for optimization, for the solution of differential equations, for factorization, and for machine learning. And in all these areas exists research which indicates that there's promising that there are promising areas where a quantum computer can prove advantageous in the end. Okay, with that, I come to the part computing with real quantum hardware. And what do we do? How do we combat errors on a quantum register? So, okay, we've already heard the noisy intermediate scale quantum device is the current state of art, current state of the devices that are being investigated, and that the run is on for quantum advantage, that for the super polynomial speedup, which proves reliable on a quantum computer. And in the long run, what we want to achieve is a fault-tolerant computer. Now, what is that supposed to be? This means that we will never be able to reduce errors on a quantum system completely, because it will always interact with the environment, and this will always cause the information to decohere and errors to come into our calculation. And also, if we want to control it and measure it, we want it to interact with the environment, right? So we will also introduce errors by this. And so this is, in the long run, we want to achieve a quantum computer which is tolerant against the remaining errors which happen on it. So these are the leading hardware platform candidates at the moment. I would say superconducting hardware is in the lead in terms of being engineered by Google and IBM, for instance. There are ion traps, there are photons to be used, quantum dots where we build on existing silicon technology, cold atoms which are controlled. And we have, of course, criteria developed for these systems. So when is a qubit a qubit which can really work as a building block for quantum information? And the thing is that it has to be scalable. We have to be able to initialize it to a certain state with which we can compute. Then it has to have long coherence times, so the information has to sit there for a while on the qubit, reliable. And then we need a universal set of quantum gates, where universal means that from this set of gates, which can be executed on this specific hardware, we need to be able to map all quantum operations which we want in principle, can in principle do, need to be able to map this to this set of gates. And then, of course, we need to be able to measure it. Okay, so what are the challenges about that? So the challenge is, on the one hand, that we will always have a limitation on the gate fidelities, because errors during control operation will always happen. Then the second challenge is that we have a limited set of so-called native gates on the physical systems, which need to be, in the end, a universal set of gates. A native means that these are gates which exist on the system and which we can do in a controlled way. And we have a limited connectivity among the qubits. Every quantum system, the part of the system see only a part of the other qubits, and this can differ quite a lot from the ideal quantum computer where every qubit sees the other. So we have all-to-all connectivity on an ideal quantum computer, which does not exist in reality. Then all quantum information decoheres due to its interaction with the environment. And then we have the problem of scalability, which does not in principle mean that it's so difficult to just build more qubits, but it's difficult to build them in a way that they are still, that the error on them is still quite low, and that we do not introduce strong control errors. And I brought you the sketch from the New Yorker about the current state of quantum computers. Okay, so I will now introduce a specific system to you. This is building a quantum computer from diamond. So I will talk about the defect-based system, which has been researched intensely in the context of quantum sensing, so kind of another quantum technology which is extremely sensitive towards magnetic fields, and it's currently being explored as a quantum register, where the hope is that in the end we at some stage will be able to use it as a quantum memory. So in a diamond lattice composed of carbon-12 atoms, one carbon-12 atom has been replaced, in this case by a nitrogen atom, and its nearest neighbor site is vacant. And this is a spintronic system, which means that we use the spin of the system to control it and to use the spin of the system as a qubit. So the electron spin of the vacancy center is a triplet and is one building block for a qubit. And it couples. I will now be a bit more physical, and don't worry if you don't understand everything. I will switch back later to being much more understandable in 2 minutes or so. But maybe there are physicists among you who want to know a bit more details. So by a hyperfine interaction, the spin couples to the surrounding nuclear spins in the material, to the carbon-13 isotopes, which are there in the material with a natural abundance of 1.1%. And it couples also to the intrinsic spin of the nitrogen atom, which also forms a triplet. And the carbon spins are duplets. So here we have a clear defined qubit, and in the other two cases we have to choose our qubit levels. So we can execute gates with microwave pulses on the electron spin and radio frequency pulses on the nuclear spin. And we have a central spin system connectivity, and here you can very clearly see that this is far away from all-to-all connectivity, because all interactions have to be mediated by the central electron spin, because the coupling among the nuclear spins here in the outer shell is not strong enough to be taken into account. The system is scalable either by coupling more carbon isotopes to it, or by coupling the central electron spin of several registers, either by dipolar interaction, where we have to have two very, very close, on a nanometer scale, two very close systems, or by photomediated long-range interaction in a planar waveguide. And yeah, basis gates are very nicely. They are just rotations around the Bloch sphere, which means we can map any gate easily. And we have very long coherence times, especially on the nuclear spins, which sit in a very stable lattice in the diamond. And it's operational up to room temperature, with a strong contrast to the superconducting hardware, which is operated a few millikelvin away from the absolute 0 point. Okay. So how do errors on a quantum computer occur? I've mentioned this already. We have a quantum computer, and it interacts with the environment. And one part is that we want to control the interaction, so we want it to interact, and we have errors during this control operations. And the other part is that there's undesired interaction, which will always cause our information to decohere. For instance, if we have this NV center, which I've just shown to you, then there will other spins in the environment which we cannot control, will interact with the central electron spin and cause it to decohere. And then we have errors during two qubits interaction, so our qubits will interact with each other and control errors or unwanted interaction errors, and will also cause information to decohere. However, we also need them to interact, and this will also introduce errors. So there are two strategies to deal with that. The one hand is to reduce the errors on the control operation and to shield them as much from the environment as possible. For instance, in this case, by making the material isotropically pure. And the other one is that we have remaining errors, and we deal with these remaining errors. On the one hand, we can deal with them with error mitigation, which Jens Eisert mentioned this morning. And on the other hand, we can deal with them with quantum error correction. And quantum error correction will, in the long run, such as the hope, lead to fault-tolerant quantum computers. And I will introduce both strategies now briefly to you. So this will, again, be a bit more physical, the part. So we have the energy diagram of the system I've just shown to you, and we've already identified two levels of our triplet spin. So the 0 level and the -1 level as our qubit levels. So this is the central electron spin. And then you can see that this energy diagram splits up. And we take into account the intrinsic nuclear spin, the nitrogen nuclear spin. And then we define the 0 and the +1 level of this as energy levels. So we look at 4 distinct qubit levels here, right? And these are the 2 transitions which are relevant for driving a controlled NOT operation, where we flip the electron spin conditioned on the state of the nuclear spin being 0 or being 1. And this here is the spectrum, the energy spectrum from this transition, where you can clearly see in the resolution that all 3 energy levels are available. So at different frequencies, this here shows the frequency and this the probability to find the system in the state. And you can see that we have different frequencies where we can address the system. And now we introduce a driving field with a microwave driving field, where this transition here, this omega naught transition, here mirrors exactly this energy difference. And with this, we can introduce a conditional flip of the electron spin. However, this comes at one downside, and you can clearly see that these lines, they are not absolute discrete lines in space, but they are broadened. And on the one hand, they are broadened by the intrinsic probabilistic nature, by the uncertainty principle, which means that if we want to look at the system in a specific energy and at a specific time, we will never be able to do that because these are complementary observables. And this means that if we look at a certain time, the system is not precise in energy. And due to this, we get a natural line width broadening here, so we are not very concrete at one frequency. And the difficulty is that the stronger, so this is the strength of the driving field which we have, and the stronger you drive, the better, because then the faster you get operation. And you need it to be fast, because otherwise the qubit decoheres. But if we drive strongly, we will broaden these lines out further, which is called power broadening. And then we have an overlap between the lines. So if you drive the system, you have a certain probability that you will also hit the other transition, and you don't want that. And this is what you see here in this plot. This plots the average gate fidelity, which means that we take the average over all input states of the gate, how it works, and we compare it with the ideal C0, which I've just introduced to you, and this is our faulty operation. And then you can see that when we drive in a very, very weak strength here, close to 0, we will have an acceptable number of 1. 1 is good. 1 means that we don't have any errors. And the stronger we drive, the better for the faster gate operation. But you see that in all 3 systems which we've plotted here, the error increases very quickly, and it goes up to almost complete randomness here. So this is, of course, not an acceptable operation. And what then we came up with in our latest paper, which I showed to you here, is a synchronization idea, is that you use synchronization effects between the transition that you want to drive, and now you reimagine this Bloch sphere, which I've shown to you. If you want to flip the qubit, you flip around the sphere, you flip the vector just by an angle of 180 degrees. And then you just choose your driving strength such that the transition which you've driven off resonantly, and you've also driven it just a little bit, just tiny circle on the Bloch sphere, that this performs exactly a full cycle and in the end comes back to a 0 operation. So you use these synchronization effects to find that there are driving strengths which enable a fidelity where you have completely erased this error. Okay, so we can come back later if there are questions on this. This is just to give you an idea. We can also include this into more complex schemes, which also involve control operations on the electron spin, which help to decouple from the noisy environment, which you can, for instance, do by flipping the electron spin with interpulse spacing, which the length you can vary, and you can flip it back and forth, and this helps to decouple it from the noise that is induced from the environment from the other spins. Okay, so with that, I will come to the second part. which is the part on quantum error correction. And here we want to deal with the remaining errors on the system. And the goal is in the end to construct the so-called fault-tolerant quantum computer, where we can perform a nearly faultless computation on it. And I will start with introducing a classical, so this is not yet quantum mechanical, an error channel here. So we have a bit which is sent with either 0 or 1, and we receive this bit. And with a certain error probability p, this bit will flip here. And the idea of this classical bit flip code is that we protect it against this loss of information by repetition. So we create redundancy. And this means that we encode just our qubit by copying it 2 times. And then we state that we want to look at one error which is happening, because we say against this, the error, if it's very small, then p squared will be very, very small, and we try and neglect that. So this is what happens here. We have the bit, we do the encoding, then errors happen with a certain probability, and then this is the result. And we take just the most likelihood decoder, so we use a majority vote, and deduce from the majority of the remaining bits if it's a 0 or 1. So with the probability for no error or for 1 error, we are correct, and that means that the probability for incorrect decoding remains for 2 or 3 errors. And from this, we can deduce our code threshold. And our code helps if we are with an error rate above, so our error rate is larger than the code threshold. And in the case of the bit flip code, this is 1/2. So the interpretation is that after, for p 1/2, everything is random, and we cannot improve anything anymore. So this is a classical example. And now we get to the challenges of quantum error correction. So first we have the no-cloning theorem. So we cannot just repeat the state. We cannot copy a quantum state. If we copy a quantum state, we destroy it. The second problem is that our errors have to be discretized because of the intrinsic nature, probabilistic nature of a quantum system. They do not occur just they occur or not, but they occur with a certain probability. And this means that we have to deal with a continuous probability of errors. The third problem is that if we measure the quantum system, we destroy it. But we don't want to destroy it. We want to continue our computation. And the fourth problem is we do not only have the probability for the bit to flip, but we also have the probability for the phase to go wrong, because we are in a complex state space. And I will show you a very easy, simple example, the quantum bit flip code, just as to illustrate how this kind of encoding works and how we can deal with all these problems. We can, in fact. So the first is we encode by entanglement. So our 0 becomes 0, 0, 0, and the 1 a 1, 1, 1. And please note that this is not cloning, as if we take this state space to the logical state space here, this is absolutely not equal to just 3 times copying our qubit. But we create entanglement, so we combat errors with entanglement. And the measurements are done by introducing auxiliary qubits, where you can see the circuit for such an auxiliary qubit here. So this is initialized in the 0 state, and an application of Hadamard gates and a controlled operator. And then if you measure the auxiliary qubit, you get the eigenvalue of this operator of the state in which this qubit is in. So you look at a second qubit where you can destroy the quantum information and get more information about the actual qubit you want to have, and you do not destroy the computation. And this means that we discretize the errors, because a measurement always collapses the quantum state, if you remember, to the certain outcome that we want to measure. So we have discretized the error, and with the discretization, we have brought it into rectangular state spaces to the code qubit, and from there we can bring it back to the code space. So this is how the 3-qubit repetition code looks like. We have the state, which we want to encode. We do the encoding by creating the entanglement to the 2 further code qubits. Then we assume that noise happens, and then we make our measurements with the introduced auxiliary qubits here, which we also entangle with the code space, but these ones are measured. And that, from the classical result, we can induce the correction action which we need to take on our code. And then, if only 1 error has happened, we know that we are in the correct code space again. And this is the code, same code, but just by a change of basis, we achieve to correct it not for a bit flip, but for a phase flip. And together with, if we concatenate these two codes, we achieve with 9 code qubits and a few more ancillas, we achieve 1 logical qubit, which is fully corrected against phase and bit flip errors. So this is the idea of quantum error correction. Sometimes it's just not working. And this is just to give you a brief idea about how complicated it gets when you have these codes and want to map them on a real system, because this is, again, the connectivity of this nitrogen vacancy center in Diamond that I've just introduced to you. And you can see that despite the fact that we have a very favorable set of basis gates, which allows us to compute basically any code, we have to mediate all interactions over the electron spin, and the code gets very messy, and it will certainly introduce further errors and will certainly not end up in correcting it fully. So this is one type of problem that you have when you're doing quantum error correction, that the code, in the way that it's described, needs to fit the geometry of the device you're working with. And the idea of fault-tolerant quantum computing is that, you have this logical error rate, which we've just discussed in case of the classical code. So we still have a certain logical rate with which our code fails. And just jump with me here, due to reasons of time. If we have one error correction of the code, then we have a very simple formula where we can deduce our code threshold, where C is just a constant depending on the set of gates that you use as a overhead. And then the fault-tolerant threshold theorem states that if our physical error is below this error rate, that we can, a quantum circuit with n gates, simulate with an arbitrary low error of epsilon of at most a polylogarithmic overhead, which in good English means that nearly noise-free quantum computation is possible with a moderate qubit overhead. And this is proven on paper. And this is the hope that in future, our quantum computers, when we can build a lot more qubits, can make it possible to push the error arbitrarily low on a computation. And this means that we build gadgets, and the gadget is constructed in such a way that an error occurring on it will not spread to the next gadget. So this is the principal idea. And currently, we as Jens Eisert mentioned this morning, we have on superconducting qubits, we have the surface code, and the surface code is depicted here. And as you can see, it works very nicely with a planar grid with a nearest neighbor connectivity on it, which is given by superconducting qubits. And this, again, is due to kind of how they can control it and how they build their wires. So this has been the absolute leading candidate for a while because it has a very high threshold of almost 1%, which is really high. So it tolerates almost 1% of physical errors and can push them arbitrarily low. And it has been implemented in experiments. However, it has a problem. The problem is the trade-off that if you want to go to higher code distances, which means that the error corrected, that it also corrects for more than one error, and you will need that when you go to larger computations, that your overhead scales quadratically. And this means that we are very quickly at very, very high numbers of auxiliary qubits that we need in order to just compose one logical qubit. And this is why the searches for alternatives are currently on, and you can see here a higher dimensional low-density parity check code. In principle, this means that we have a constant encoding rate on it, so it will not grow when you go to higher distances. And yeah, it looks very complicated. And the problem is that if we want to map a 5-dimensional code to 3D in a real physical system, then we need a long-range connectivity. And this is, again, difficult to provide at the current state. Other codes are dynamical codes, where the code space changes repeatedly over time. So like a Floquet system, it repeats itself in a circle. And this is also kind of brand new in the last years and a promising candidate. Yeah, and with that, I'm at the end. So I show to you how, in theory, a quantum operation works and reminded you a bit of the postulates of quantum mechanics. We looked at noise intermediate scale devices, in particular at the nitrogen vacancy center in Diamond. And then we looked at just one type of gate error that can occur and at ideas how you can avoid it. We looked at quantum error correction for the remaining error, how complicated it gets when you map this to a real system, and further ideas of current research. And I thank you very much for your attention.
Thanks again, Regina, for both the introduction and the deep dive into the real challenges of quantum computing. Maybe let me start off the Q&A with one of more small questions from me. You mentioned a couple of challenges with actually implementing quantum computers, like decoherence, scalability, and such. Which of these do you think is the most hardest to break through, and which of these may be related would you like to solve?
Well, I don't think that you can really isolate one of these challenges. So, for instance, scalability. If you scale up, then the entire system gets a lot more error prone. So we saw this morning in Jens Eiser talk the 1,100 something quantum computer which IBM has just released on the cloud. The thing is, it is there, and it's great that it's there, and it's big, but the error rates are much higher than the small one, which they already have engineered towards a point where you can do a reliable computation if you use the mitigation a bit. So it's very interwoven, and for some systems, the connectivity is not an issue. For instance, the trapped ion, you can shuttle them around, and they connect with an all-to-all connectivity, but then again, a trap is kind of limited to 20 ions, maybe a bit more. And then it's really an issue to how do you scale up. And so, yeah, each hardware has their own difficulties. So
you already know the correct consultant answer. It depends, and it's very complicated.
Thanks for your talk, and I've got one question. What's the largest number that could be factorized right now with quantum computers?
Very hard to implement. It's one of the most difficult algorithms that you can do, phase estimation on a real quantum computer, because it's very sensitive towards errors, and it's expected to become a reality once computers are constructed to be fault-tolerant. So this is, I mean, it's really difficult to say when we're going to be able to really factorize a significant kind of number which really or when are we going to be there that it really threatens encryption? You will definitely need an overhead of millions of qubits which really work well and see each other. So, yeah.
And just to get an impression about the size of numbers that could be factorized right now.
And then you can break our encryption. No, not right now, but if it works.
Yeah. And right now, is it 15 or?
Yeah, it was something. It was just a 2 by 2 number, so it was just one factorization, I think, state of the art. And it was not done in any way. It was just demonstrated that they can execute it on a computer.
Okay.
So this is not. We are not at that stage where this is really happening.
So still
other
less than
algorithms
100.
are much better suited for this for nowadays computers, and these are algorithms where you repeatedly measure again and again. For instance, optimization algorithm, because that makes use of the relatively short coherence time of the system. Then you measure, you interact again with the classical computer, and then execute the algorithm again. And this is not Shor's algorithm, so. Yeah, so it's probably not going to help you to get an idea of the progress of the field, but yeah.
Okay, thanks.
I hope that helps.
First, no questions from the web, so we have another question here.
Thank you for your presentation. The thing I really don't get is how can I use error correcting bits by entangling them with the bit I'm interested in, and measure this error bit which is entangled. and not mess up the state of the main bit.
Yeah. I hope I can try and explain it again. So let's jump back to this slide. So you see the circuit here, right?
Yeah.
Okay. So this is your quantum state that you have. In this case, it's a single qubit, okay? It's represented by the line below. Now, you have an operator M, and this operator has eigenvalues of plus minus 1. This is a necessity ingredient, but this is doable to formulate operators like that. And this is an entangled operation, which means that you execute this operator only if this qubit is in the state 1. And now you have an auxiliary qubit, which you initialize in a known state, in the 0 state. Then you apply the Hadamard truffle, which means you switch bases, and you're now in an equal superposition state, which means that by half of the probability you are in the state 1. And then you execute this, and then you execute the Hadamard again. So you go back to your set basis, where you have the basis of 0 and 1, which we know, the computational basis. And then you measure this auxiliary qubit. And this measurement will reduce entropy, so it will extract entropy from the system in the sense that you now this qubit will collapse to one in the measured basis. So you measure in the set basis. So this qubit now will collapse into one of this discrete basis states, right? And then you get the eigenvalue of this state. So you have extracted entropy from the system, you have discretized your error, and you know something about this state now, but you have not destroyed it. And that's the principal idea. And if this helps you to deduce an error, then you can correct and continue the computation. And you have to write it down probably to understand it fully. But I hope did it help a bit? Or?
Yeah, I think so. The main idea is I flip the error bit depending on the actual...
Exactly.
Yeah, that makes sense. Okay.
So in this type of code, you assume that you have a wrong flip, right? So you encode this in code space, which is 3 qubits. And then here happens exactly what I've just explained to you in a more simple form, but you need 2 auxiliary qubits in order to deduce every single error in a reliable way. So, and then you measure these 2, and by the measurement results, you can deduce from the classical result here on which part of your encoded state space you have to flip. And then you can decode back by executing exactly the same reversible, and then you have your single gate, which is in theory error-free, but in practice, of course, it's not error-free because you have done a lot of faulty gates in between.
Thanks.
Yeah.
I don't know which one of the two of you came first, so sorry, I'm going this way. I'm sorry.
Can you explain a little bit more the synthesis of the diamond qubit and how can you control the number of nitrogen defects and the position?
I hope I can, as a theorist. You cannot yet really control unfortunately, there's intensive research going on because the thing is, if you want to scale up by dipolar coupling, they have to sit in a proximity of nanometers towards each other because dipolar coupling decays very quickly. And this is not yet doable, but there is research going on. What is currently done is that you grow them in a way that this nitrogen grows into it. I think randomly, only controlled by the abundance of the material during the growth process, and then you search for reliable systems where you have to take into account the axis, the proximity to the surface, and also if you want to scale up by this, the axis towards each other, right? Because the system axis, if it's too much tilted, then you cannot ignore that there's also a perpendicular component of the hyperfine interaction, and then it all gets very faulty. So I've spoken to an experimentalist who says they scan about 1,000 probes until they find one system which is okay. And then starting from there, you start searching with the scanning mechanism, with the sensing mechanism, this intrinsic sensing mechanism of the system, that you see really the magnetic field by hyperfine interaction. Then you search for the surrounding carbon isotopes in the material. Yeah, and so one of the leading experimentalists explained to me that they can do 70, which is quite a lot, but of course they cannot simultaneously control 70. Yeah.
I think this will be now the last question. It relates to the previous one.
Oh yes, it's just about the error correction. So I was wondering, you need like mid-circuit measurement for the error correction codes, and in the nitrogen vacancy-based computers, are there already systems that allow for mid-circuit measurement?
Yes, there are. So it's also doable on the nitrogen vacancy center. Yeah, this is a question of enabling technology, so of the how quickly you can process the signal. And yeah, so IBM, for instance, also allows for mid-circuit measurements. And there are also, because this is a very interesting question, there are also a lot of codes who decode in such a way that it's possible to do your decoding at the end of the computation. So, which means that you do not need to process the signal at the same speed where your computation happens, but you can just store it, and then in the end, look at all the measurements, and from that deduce the errors that you have to correct on your result in order to get the correct result. And this is always doable when you only store a qubit, because this is a theorem by the gates that you need for this. So if you only store it, if you only put it into, you get the information, you put it on a nuclear qubit, you want it to sit there because it would sit there for days, and then you would like to keep this in a correctable way, then you can do it like this as well. You don't have to disturb your system by measurements all the time, and by controlled action back, you have to do the measurements, but you don't have to disturb it by the controlled actions on it again. You can do this in the end.
Okay, thank you.
Welcome.
Thanks again for all questions. Thank you all for coming to this talk, and thanks, please, one more time for Regina. Great to have you here.